Dear students, I am Hiba Haq, lecturer of physics from Government Degree College, MALIR, KANTT, Karachi. My this lecture is about heat and the first law of thermodynamics, which is a topic from chapter 11, intermediate Sindh textbook. So in this topic, I shall explain what is heat capacity, specific heat capacity, and molar heat capacity. After that, what is thermodynamics? Then I will drive the expression of a work done in changing the volume of a thermodynamic system. After that, I will explain the first law of thermodynamics, and then the applications of first law of thermodynamics, and at the end I will drive certain expressions that include Cp minus Cv is equals to RT, V to the power gamma minus 1 is constant, and PV to the power gamma is constant. Okay, let's start with heat. Heat is defined as the form of energy that flows between a system and its surrounding or environment by virtue of a temperature difference between them, or when an energy transfer takes place by virtue of a temperature difference exclusively, it is called a heat flow. It is denoted by Q. So here is a diagram in which we have two bodies A and B. Temperature of body A is Ta, temperature of body B is Tv, such that temperature of body A is greater than temperature of body B. When these bodies are placed in thermal contact with each other, heat will flow from body A to body B till the temperature of both body become equal. Now, if Q be the amount of heat energy transferred by virtue of temperature difference delta T, experimentally it is found that this amount of heat energy is directly proportional to the total mass of a body. Mathematically, we can say that Q is proportional to M. I mark it as equation number 1. And the total amount of heat energy transferred is directly proportional to the temperature difference or rise in temperature. So Q is proportional to delta T. I mark it as equation number 2. If we combine equation number 1 and equation number 2, we get Q is proportional to M delta T. Removing the sign of proportionality and introducing a constant C, we get Q is equals to MC delta T. So this formula shows the total amount of heat energy transferred from hot body to cold body due to the temperature difference delta T. This constant C is known as specific heat capacity, and it depends upon the nature of a material of the body. Heat energy is measured in joule or calorie, and 4.2 joule is equal to 1 calorie. Okay, so if we talk about heat capacity of a body is the ratio of the amount of heat supplied to a body in any process to its corresponding temperature change delta Q, or we can say that the heat capacity of a body of any kind is defined as the heat required to raise its temperature by 1 Kelvin. It is denoted by C prime, and its formula is Q upon delta T. Heat capacity is measured in joules per Kelvin. Okay, if we talk about specific heat capacity, the heat capacity per unit mass of a body is known as specific heat capacity, or the specific heat capacity of a substance is defined as the heat required to raise the temperature of unit mass of it through 1 Kelvin. Specific heat capacity is denoted by C. So C is equal to C prime upon M according to the definition, or we know that C prime, that is heat capacity, is Q upon delta T. So C specific heat capacity is equal to Q upon M delta T. It is measured in joules per kilogram into Kelvin. Now if we talk about molar heat capacity, it is the heat capacity per unit number of moles of a substance Or we can say that the molar heat capacity of a substance is defined as the heat required to raise the temperature of 1 mole of it through 1 Kelvin. It is denoted by C, and C is equal to C prime upon N according to the definition, or C is equal to Q upon N delta T. It is measured in joules per mole into Kelvin. Okay, so thermodynamics. Thermodynamics is the branch of physics that deals with the laws governing the conversion of energy to and from heat, and the methods used for such transformation. So if we talk about a thermodynamic system, we have to define a system. A system is a collection of matter which has a distinct boundary. For example, gas enclosed in a cylinder fitted with a piston. We have three types of systems that are closed system, open system, and isolated system. If we talk about closed system, a system in which there is no transfer of mass across its boundaries. A gas enclosed in a balloon or cylinder forms a closed system. Open system, a system in which mass may enter or leave the system. For that we have plants and animal. And isolated systems are those systems in which there is no transfer of mass and energy across its boundary. Now, if we talk about surrounding, everything other than the system which has direct effect on the behavior of the system is called as surrounding. Okay, so here is a example of a system, a gas filled cylinder. So this gas is actually a system, and the walls of these cylinders are the system boundary, and the region around this cylinder is the environment or surrounding. I have already explained what is open system, closed system, and isolated system. So for if we talk about open system, these are those system in which matter and energy can transfer from system to surrounding or from surrounding to system. So if we talk about closed system, only energy can transfer from system to surrounding or from surrounding to system. And for isolated system, there is no transfer of matter or energy from system to surrounding or from surrounding to the system. Okay, now let's talk about work in changing the volume. For that, we have to consider a thermodynamic system. A thermodynamic system consists of an ideal gas enclosed in a cylinder fitted with a frictionless piston. The walls of the cylinder and piston are made up of insulating material, that is non-conducting material, while base of the cylinder is made up of perfect conducting material. So here we have a cylinder fitted with a piston, and an ideal gas is enclosed in it. So these are the walls, insulating walls of the cylinder, and this is the conducting base. This is the movable piston, and then this is the piston rod. So this piston will respond quickly on a very small variation. Now we have system boundary and then surrounding, and through base heat can enter or leave the system. And what we do, we just place a small amount of weight on a piston to create a pressure on the gas. Okay, so let us assume that in equilibrium state the gas occupies a volume V0 and exert uniform pressure P on the cylinder's walls and piston. If A be the area cross section of the piston, the force exerted by the gas on the piston will be, we know that pressure is force per unit area, so force will be equal to pressure into area. Now if we remove the weight from the piston, the external pressure of a gas reduces and the gas expands slowly till it achieves equilibrium state. By equilibrium we mean that the internal pressure of a gas and external pressure become equal. So let us assume that the piston moves a distance delta y as shown in figure 1. So this is the initial state in which the volume of a gas is V0 and pressure is P. So when we remove this weight, the gas will expand to a displacement delta y, and for that the volume of a gas changes from v naught to v, but the pressure will be same, that is p. Okay, we all know that work done performed by the gas on the piston will be force into displacement, or force is equal to pressure into area. So work done will be equal to pressure into area into displacement, where area into displacement is change in volume. So work done is equal to pressure into change in volume. So here is a graphical representation. We draw a graph between P and V such that V is along y-axis, x-axis, and P is along y-axis. So if we draw a graph, we get a hyperbolic shape, and the area under this curve is the work done. And this diagram is also known as PV diagram. Okay, now I will explain the first law of thermodynamics. And the statement of this law is the increase in energy of a system is equal to the energy flowing in as heat minus the energy flowing out as work, or the heat energy supplied to a system is equal to the increase in internal energy of a system plus the work done by the system on its surrounding. Or we can state it in this way, that the heat energy is converted into other forms of energy, or other forms of energy can be converted into heat energy, but the total amount of energy of a system remains constant. So this is similar to the conservation of energy. So basically, first law of thermodynamics, energy transformation means that energy before the transformation and energy after the transformation should be equal or balanced. So if delta Q amount of heat energy is added to any system, the heat energy is partly appears as an increase in internal energy delta U stored in the system, and partly as the work done delta W by the system on the surrounding. So delta Q should be equal to delta W plus delta U, and we know that delta W, that is work done, is equal to P delta V. Delta Q is equal to P delta V plus delta U. So for an isolated system, delta Q and delta W are zero, as there is no exchange of matter and energy from system to surrounding or surrounding to system. So the internal energy of a system remains constant, and for a cyclic process, change in internal energy is zero. So dealing final expression for the first law of thermodynamics, you need to memorize these things, that change in heat delta Q is greater than zero or positive when heat enters the system, or delta Q is less than zero or negative when heat leaves the system. If we talk about work done is greater than zero or positive when work is done by the system, and delta W is less than zero or negative when work is done on the system. If we talk about internal energy, delta U is greater than zero or positive when the temperature of the system rises, and delta U is less than zero or negative when the temperature of a system falls. And change in volume is greater than zero or positive when the gas in the cylinder expands, and delta V less than zero or negative when the gas in a cylinder compresses. Applications of first law of thermodynamics. In applications of first law of thermodynamics, I will explain isobaric process, isochoric process, isothermal process, and adiabatic process. So in each process, we will apply first law of thermodynamics and try to find the final expression. So let's start with the first application, that is isobaric process, and it is a process which take place at constant pressure. In such process, heat transferred and work done are both non-zero. Now consider a system consisting of an ideal gas enclosed in a cylinder fitted with a frictionless and movable piston. Let delta Q amount of heat energy is transferred from surrounding to the system. The gas expands such that the external pressure P remain unchanged. So here is a diagram in which this is the initial state of gas. Let it is at initial volume V, and the pressure, external pressure is P. If delta Q amount of heat energy is supplied, let its volume changes, the volume of gas changes to V2 because of expansion, and the piston displays to a distance h. So in both states the pressure, external pressure, remains constant. The work done by a gas in moving a piston of area A to a small displacement is given by delta W is equal to P delta V, where delta V is the increase in the volume of a gas. Since the gas is expanding, so delta V is positive. Now, according to first law of thermodynamics, delta Q is equal to delta W plus delta U, or we can say that delta Q is equal to P delta V plus delta U. So if we plot a graph between pressure and volume for isobaric process, it is of straight line. So we conclude that for an isobaric process, the amount of heat energy supplied to any system is equal to the increase in internal energy, that delta U of the system, plus the work done by the system on its surrounding. The second application of first law of thermodynamics is isochoric process, and it is a process which take place at constant volume. For isochoric process, the heat transfer and internal energy are both non-zero. So the volume of a gas should remain constant. For that, we consider a cylinder fitted with a piston containing a certain amount of an ideal gas. Let delta Q amount of heat energy is supplied, keeping the volume of a gas fixed. For that, we seal the piston. The best example for isochoric process is your pressure cooker. During this heating, the pressure of a gas increases or changes from Pi to Pf, let's suppose. And since there is no exchange in volume, for that, work done is zero. As we know that work done is equal to P delta V. So if the pressure volume of a gas is constant, delta V is 0 and delta W is 0. So here we have a cylinder whose initial volume and final volume both are equal, and we supply delta Q amount of heat energy to this system, and for isochoric process, work done is 0. Okay, according to the first law of thermodynamics, delta Q is equal to delta W plus delta U, and for isochoric process, delta W is 0, so delta Q is equal to delta U. So for an isochoric process, the amount of heat energy supplied to any system is utilized in increasing the temperature of gas molecules or increasing the internal energy of a system. So I haven't explained the graph in previous diagram. So if we plot a graph between pressure and volume such that volume along x-axis and pressure along y-axis, for isochoric process we get a straight line parallel to y-axis. The third application of the first law of thermodynamics is isothermal process, and it is a process which takes place at constant temperature. For isothermal process, heat transferred and work done both are non-zero. So let us consider a system consisting of an ideal gas enclosed in a cylinder fitted with a frictionless and movable piston. A cylinder has heat conducting base and non-conducting walls and piston, and we place this cylinder on a heat reservoir or a hot body. So if the pressure of the gas in the cylinder is decreased by decreasing the weight on the piston, the gas expands, and due to expansion the temperature of gas falls. To maintain the temperature of a gas, the hot temperature reservoir or heat reservoir will supply delta Q amount of heat energy to the system. so that the temperature of a gas remain constant, that is Tf is equal to Ti. And if the temperature of a gas is constant, it's mean that internal energy, change in internal energy is constant, zero. We are not talking about the internal energy of a gas, we are talking about the change in internal energy. So internal energy of a gas exists, but the change in that energy is zero. So here we have a diagram in which initial stage we have pressure, volume and T, and when if we remove the temperature, sorry, if we remove the weight from the piston, the gas will expand, but due to the heat reservoir, the temperature of a gas is constant. According to the first law of thermodynamics, delta Q is equal to delta W plus delta U, or for isothermal process, delta U is 0, so delta Q is equal to delta W. We can say that for an isothermal process, the amount of heat energy supplied to any system is utilized in performing work done. And the graphical representation for isothermal process is hyperbolic shape. We plot a graph between volume and pressure, we get a hyperbolic curve, and the area under this curve is work done, which is greater than 0. The last application of the first law of thermodynamics is an adiabatic process, and it is a process in which no heat flows into or out of the system. For an adiabatic process, the internal energy and work done are both non-zero. Okay, now consider a system consisting of an ideal gas enclosed in a cylinder fitted with a frictionless and movable piston. A cylinder has heat conducting base and non-conducting walls and piston. So to stop the heat exchange, we place the cylinder on an insulator. For that, delta Q is equal to 0. Now if the pressure on the piston is suddenly increase, the gas compress rapidly, pushing the piston down, and temperature of a gas rise. So here we have a gas filled cylinder, and if we increase the pressure, external pressure, the piston will move down, and the temperature of a gas increases. Okay, according to the first law of thermodynamics, delta Q is equal to delta W plus delta U. For an adiabatic process, delta Q is 0, so delta U is equal to negative of delta W minus delta W. Or for an adiabatic process, the change in internal energy of a system is equal to negative of work done. So this is the graphical representation of adiabatic expansion. I have explained you the adiabatic compression, that is the compression of a gas without the exchange of heat energy. So if we talk about expansion, when we reduce the pressure on the piston of a cylinder, the gas will expand, and as the gas expands, the temperature of a gas falls. So the graph is between V and P, pressure and volume, and here we have thermally insulating walls, no exchange of heat. So this is all about the applications of first law of thermodynamics. Okay, in the end, I will drive few relationships. The first one is Cp minus Cv is equal to R, or Cp minus is greater than Cv, where Cp is the molar heat capacity at constant pressure, and Cv is the molar heat capacity at constant volume. So, and let's start by considering a number of moles of an ideal gas contained in a cylinder fitted with a frictionless and non-conducting piston. If the piston is fixed and the gas is heated, its volume remains constant, and heat supplied goes to increase the kinetic energy, which is the internal energy of the molecules, due to which the temperature of a gas increases. If delta Q be the amount of heat energy supplied and delta T be the increase in temperature, then by using the definition of molar heat capacity at constant volume, we can say that Cv is equal to delta Q upon N delta T, or delta Q is equal to NCV delta T. The final expression of first law of thermodynamics for isochoric process is delta Q is equal to delta U. So for isochoric process, delta W is 0. We just put the value of delta q in above equation. Delta u is equal to ncv delta t. I mark it as equation number 1. Okay, now if the piston of the cylinder is free to move up and down, the same amount of heat delta q is supplied to the system, and gas is allowed to expand in such a way that the pressure of a gas remains constant. So the heat energy supplied is partly used in rising the temperature of a gas, that is delta T, and partly used in doing work, that is delta W. So by the definition of molar heat capacity at constant pressure, Cp will be delta Q upon N delta T, or delta Q is equal to Ncp delta T. So the final expression for the first law of thermodynamics using isobaric process or for isobaric process is delta Q is equal to delta W plus delta U, where delta Q is equal to Ncp delta T. So we can say that delta W plus delta U is equal to Ncp delta T. We all know that delta W is equal to P delta V, which is equal to NR delta T from general gas law. And from equation 1, delta U is equal to NC V delta T. So we put the value of delta W and delta U in above equation. NR delta T plus NCV delta T is equal to NCP delta T, or by taking the constant N, by taking n delta t common, we get n delta t is into r plus cv is equals to ncp delta t. This delta t cancel and n cancel, so we get r plus cv is equals to cp, or we can say that cp minus cv is equal to r. So since cp is equal to cv plus r, it means that cp is greater than cv, where r is the universal gas constant. So the difference between cp and cv is equal to universal gas constant r, as r is the positive quantity, hence the molar heat capacity at constant pressure is greater than the molar heat capacity at constant volume. Okay, at the end I'm going to drive TV to the power gamma minus 1 is constant and PV to the power gamma is constant, where this gamma is Cp upon Cv, that is the ratio of molar heat capacity at constant pressure to the molar heat capacity at constant volume. So consider a small change of state in which temperature changes delta T and volume delta V. For an adiabatic process, delta Q is 0. According to first law of thermodynamics, for an adiabatic process, delta U is equal to minus delta W. And in any process of an ideal gas, delta U is NCV delta T. We already find it. And delta W is P delta V. So we can say that NCV delta T is equal to minus P delta V, or in this expression, according to general gas law, P is equal to nR T upon V. So NCV delta T is equal to minus nR T delta V upon V. This n will cancel. CV delta T upon T is equal to minus R delta V upon V. And we know that R is equal to Cp minus Cv. So above equation changes to Cv delta T upon T into minus Cp minus Cv into delta V upon V. Or we can rewrite it as Cv delta T upon T plus Cp minus Cv delta V upon V is equal to 0. Divide the above equation by Cv. Delta T upon T plus Cp minus Cv upon Cv into delta V upon V is equal to 0, or delta T upon T plus Cp upon Cv minus 1 into delta V upon V is equal to 0. So Cp upon Cv is gamma. Equation changes to delta T upon T plus gamma minus 1 delta V upon V is equal to 0. Now we integrate this equation. If we integrate 0, we get constant. I used ln c, and using this relationship ln dx upon x is equal to ln x. So integration of delta t upon t is equal to ln t plus gamma minus 1 into ln v, or we can rewrite it as ln t plus ln v to the power gamma minus 1 is equal to ln c. Since ln a plus ln b is equal to ln a into b, so ln t into v gamma minus 1 is equal to ln c. Now taking anti-log on both sides, tv to the power gamma minus 1 is constant. Now from general gas law, pv is equals to nRT. So if we get t from this equation, t will be equal to pv upon nr, and then v gamma minus 1 is equal to constant. So p v to the power gamma is equals to nr constant, basis same, power add. So gamma minus 1 plus 1 will be gamma, and n is the number of mole which is constant, r is universal gas constant. So if we multiply it with constant, we get constant. p v to the power gamma is equal to constant. So this is all about today's lecture. In my this lecture, I initially define heat capacity, then specific heat capacity and molar heat capacity, and then after that I explain thermodynamics and system, its types, and what is surrounding. After that I explained the first law of thermodynamics, which is one of the most important topics from your course outline, and the applications of first law of thermodynamics, and in the end I derived Cp minus Cv is equals to R, and Tv to the power gamma minus 1 is equal to constant, and Pv to the power gamma is constant. So the purpose of my these online lectures is to provide you some amount of material that will help you to prepare yourself for your final exam. So at the end I just want to say that good, better, best, never let it rest till your good is better and your better is best. Thank you. If you have any question, feel free to ask. I will try my best to answer them. Take care. God bless you.